Hello students. Today let us start with chapter 14 Oscillations part 1. So far we have been studying about translational motion, os- uh, circular motion, rotational motion, etc. Today we are going to learn about periodic motion. Let us see what is periodic motion. Let us see some examples. Now this graph shows an insect climbing up a ramp and falling down, then coming back to the initial point. This is repeated. The process is repeated identically, and a graphic representation is as shown in this graph. There is a periodic time over there represented by capital T, and the graph shows the height above the ground versus time. The second graph shows a child climbing up a step, coming down and repeating the process. Its height above the ground would look like that in this graph. The third example we see when we play the game of bouncing a ball off the ground between your palm and the ground. The graph shows the height of the ball versus time. And you can see the third graph, the curves are parabolic in nature according to Newton's equations of motion. Therefore, a motion that repeats itself at regular intervals of time is called periodic motion. Next, let us see what is oscillatory motion. Oscillatory motion is sometimes referred to as vibratory motion. Oscillations are a term which is given for to and fro motion of a little large amplitude. But if the amplitude is very small and the oscillations are very close together, then we use the term vibrations. In effect, both represent the same type of motion. Here we have a block attached to a spring. The other end is fixed to a rigid wall, and the block moves on a frictionless surface. The dark part of the block shows that it is extended further away from its equilibrium position and let go. Now, when it is let go, it exhibits oscillations on the surface. Finally, it comes back to its equilibrium position as shown by the blue block. That will be the equilibrium position of the block coming to rest after the oscillations. Oscillating bodies eventually come to rest at their equilibrium position because of the damping force due to friction and other dissipative causes. Another example of an oscillatory motion is the oscillation of a simple pendulum. You can see the bob suspended by a string from a wall or from a rigid support. So when the ball is pulled to one side, it will exhibit oscillations. Next, let us see some terms like period and frequency in oscillatory motion. What is period? The smallest interval of time after which the motion is repeated is called its period. And period is denoted by the letter capital T. Its SI unit is seconds. Next is frequency. Frequency is the number of repetitions that occur in unit time. It is denoted by nu. Nu is a Greek alphabet and nu is given by 1 by time period. The unit of nu is therefore S minus 1. S stands for second. So 1 by time will be 1 by second. So that represented by S to the power minus 1. Hertz is also another unit of frequency. In fact, Hertz is the SI unit of frequency. and 1 Hertz is 1 oscillation per second, otherwise represented as 1 s to the power minus 1. Next, let us see what is displacement of an oscillating particle. Now, the displacement can be represented by a mathematical function of time. In case of periodic motion, this function is periodic in time. One of the simplest periodic functions is given by the equation function of t equal to a cos omega t. Simple harmonic motion. Now this is the simplest type of oscillatory motion. So there are certain conditions for a particle to exhibit simple harmonic motion. A particle has to vibrate to and fro. You can see the diagram. A particle is vibrating back and forth about the origin of x-axis between the limits plus a and minus a. This type of oscillatory motion is said to be simple harmonic if the displacement x of the particle from the origin varies with time according to the equation xt equal to a cos omega t plus phi, where a, omega and phi are constants. A stands for amplitude, omega stands for the angular frequency, and phi stands for phase. The simple harmonic motion is not any periodic motion, but one in which displacement is a sinusoidal function of time. Now here we have the representation of displacement versus time graphically as per the equation xt equal to a cos omega t plus phi. It is a cosine function, and you know a cos function has its maximum value at 0. Cos 0 is 1. So if according to the equation omega t plus phi is 0, then we get cos 0 is equal to 1 or xt equal to a. That is why in the graph at the origin we have maximum a. So when it shows this type of graph has got omega t plus phi equal to 0. Now here once again xt is the displacement x as a function of time t. A stands for amplitude. Omega stands for angular frequency. Omega t plus phi is phase. And phi is phase constant. In this graph, the phi is also constant and t equal to constant. Therefore, omega t is 0, phi is also 0. Let us see the movement of a particle in simple harmonic motion. Here we have the particle at the position A for time t equal to 0. Now the particle is set into oscillation or in simple harmonic motion, and after 1/4 of the time period, that is small t equal to t by 4, the particle comes to the center. You can see the particle is now at the position O. After half a period, the particle goes to minus A. So it starts from A, it goes to O, and now it has come to minus A. Next, it goes back to O. So it is reversing its path. So t equal to 3/4 of the time period, the particle goes to O. And on completion of the time period, it goes back to the starting position A. So we have one full cycle or one full period. The particle starts from capital A at t equal to 0. After 1/4 of a time, it comes to the center. Then at half period, it comes to minus A. Then at 3/4 of time, it goes back to O. And at completion of one full time period, it reaches its initial position T. Now what happens for the next 1/4? For the next 1/4, it again repeats its motion and comes to O. So this is periodic motion, or this type of motion is called simple harmonic motion. So the location of the particle in simple harmonic motion at the discrete values, time equal to 0, t by 4, t by 2, 3t by 4, t and 5t by 4 are shown here. And we should note the speed of the particle is maximum at the center when x equal to 0 at the center, and minimum at the extreme positions. Here we have a graph now, a displacement time graph for two particles which are exhibiting simple harmonic motion. Now the two particles have got different amplitudes. You can see the representation of one graph by blue color. It has an amplitude A, and the other graph by the representation of black color has an amplitude B. But both are in phase, both start and stop at the same time. So we say they are in phase. And you can see both have got phi equal to 0 because they have maximum. They follow the equation xt equal to a cos omega t plus phi. Here phi equal to 0 because both start simultaneously at the origin. A is maximum value, B is also maximum value. So let us write the equation separately for the two waves. So for the first wave, that is the blue wave, we have x of t equal to a cos omega t because phi is 0. And the second wave follows the equation xt equal to b cos omega t. Now this is another example where we have two oscillatory motions. Both have got same amplitude A, but the value of phi is different. You can see the blue graph has an amplitude A and its maximum value is at the origin. So it follows the equation xt equal to a cos omega t plus phi. Phi is 0 for the blue graph. What about the black graph? The black graph does not have its maximum at 0. It has already passed pi by 4. So phi is minus pi by 4 here. So let us note the equations. X of t for the blue graph is a cos omega t. Phi is 0. And for the black graph, x of t equal to a cos omega t minus pi by 4. So these are the equations with reference to time for the two graphs, displacement time graphs that is shown here. Now here we have a third type of graph where amplitude is same for both motions, but the time period is different. Both have got phi equal to 0. You can see the black graph and the blue graph have got maximum value at the origin. Both have the same amplitude A, but time period is different for both. So let us form equations as per xt equal to a cos omega t plus phi. So x of t1 equal to a cos omega t1 plus phi. Here phi is 0, so we can also write it as a cos omega t1. And the second equation will be x of t2 equal to a cos omega t2 plus phi. Here again phi is 0. Now why is phi 0? Because we have the maximum value at the origin itself. So this is how these are three different examples of oscillatory motion where we have plotted graph of displacement versus time. We will continue in the next class. Thank you, students.